Okay, so in this video I just wanted to go through the homework that you had on chapter 21 and 22. So the first question, question 1, was a thermochemistry question. They asked you to identify the hydrocarbon gas produced by anaerobic bacterial decomposition of either animal or animal waste or vegetation. Well, that's methane. So anaerobic decomposition, methane, you're going to say there. Give a major use for methane gas. Well, methane is used as a fuel. Or do you remember in chapter 21 we talked about production of hydrogen? So we said it was either electrolysis of acidified water, or else steam reforming of natural gas. Do you remember that? So that would be another use for methane, steam reforming of methane or natural gas to make hydrogen. Okay, so that's another use there. Then it says, why is this concentration of the gas concerned in the atmosphere? Because it's a greenhouse gas, so it's contributing to global warming. That's what you need to say there. Now it says in part B then, it says the boiling points of propane and dodecane are, so propane is minus 42 and dodecane is 116. Now, propane would have a formula C3H8, dodecane is C12. H26, okay? So explain why high relative molecular masses have higher boiling points. So this has a much higher boiling point. It's the same homologous series, same family of compounds. They're both belonging to alkanes. But how will you explain that dodecane has such a higher boiling point? So you're going to say that because it's a bigger molecule, then it has more atoms, and those atoms have more electrons. The more electrons you have in the molecule, the stronger the temporary dipole that can arise, and therefore the stronger the van der Waals forces. That's what you need to say there, okay? If you've got stronger van der Waals forces in dodecane compared to the van der Waals that you'd have between propane molecules, then you need more energy to break those van der Waals because they're stronger, and therefore dodecane has a higher boiling point, okay? The next part then they asked you there, write a balanced equation for the dehydrocyclization reaction which happens when heptane, hep to C7, remember? So it's C7H16. Heptane is converted to methylbenzene. Now, trying to remember the formulas of methylbenzene is hard. So do you remember what we said? Benzene is C6H6, but if you're going to attach a CH3, then you need to get rid of one of the hydrogens. So it's actually C6H5, the methyl group, CH3 attaches on. So that's C7H8 is the molecular formula for methylbenzene, okay? So that's C7H8. So how much hydrogen then, look, how many hydrogen atoms are you going to have? So 8 from 16 is 8. So, but remember that hydrogen is diatomic, so it's 4. So that would be the balanced equation that you'd be writing there then. Okay, so to write that out, more clearly, I was just trying to figure it out there. You see 7H8 and 4H2. So that's the actual equation that you'd be getting the marks for. Okay. The next question there then that they asked you was the purpose of dehydrocyclization in oil refining. Well, dehydrocyclization is used to increase octane number or to reduce the tendency of the fuel to auto-ignite, to reduce knocking, something like that, okay? Part B then of question 1, it says but-2-ene, 2-methylbutane and a second alkene are the products of catalytic cracking of dodecane. So again, dodecane is C12, H26, okay? And when they broke that, they got but-2-ene. Now, if you're unsure, draw it out, okay? So there's but-2-ene there, okay? Put in the hydrogens now. So what would the molecular formula for that be? Count them up. C4H, how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. C4H8 is but-2-ene. Plus 2-methyl-butane. So again, draw it out if you're unsure. Butane is there, 2-methyl here, and then count out the other hydrogens. And when you add them all up and count them out, you get C5H12. So what have you got left, if you like? Okay, so add them up. So 4 and 5, so that's 9, 8 and 12 adds up there to give you 20. So by subtraction then, okay, you're going to have C3H6, okay? So that's the molecular formula. Now you were of the third product of the X there. Now you were just asked to write the molecular formula. You weren't asked to draw it or anything. So just writing the molecular formula is all there. Oh, I just actually noticed for part 1 there, look, you were in fact asked to draw the structural formula for each of the named products. So they named butene, so you would have to draw that out, and you'd have to draw out the 2-methylbutane. And don't forget, of course, to put in all the hydrogens. I'm not doing it there, but you must do it. Defining Hess's law then for part E. So it states that if a chemical reaction takes place in a number of stages, then the sum of the heat changes in the separate stages is equal to the sum, or is equal to, the heat change if the reaction was carried out in one step or one stage. Okay, so that's your definition of Hess's law. Now, they asked you then to calculate the heat change for C12H26. Now, butene is C4H8. So this actually kind of really depended on you getting the right molecular formulas at the top, or in part D. But anyway, look, so that's what you're trying to find out. Okay, so that's what you want. Okay, dodecane producing butene, 2-methylbutane, and our product X we said was C3H6. Okay, now remember how you do these again. Okay, so what equations were you given? Well, you were given heats of formations. Now remember to keep the arrows underneath each other. I'm going to do this kind of small so I can fit onto this board, but when you're trying to come up with the heat of formation of dodecane, it's C12H26, and they told you was minus 350.9. Okay, so coming up with that, what elements are present there? Well, carbon and hydrogen. Now remember that hydrogen is diatomic. 12 carbons. One second now. So 12 carbons, so 12C, and half of 26 is 13. So you'd have 13 hydrogens. Okay, the next one then was C4H8. The value for that there was minus 9.3. So coming up again with the heat of formation of that, 4 carbons this time, and again remember that hydrogen is diatomic, so that's 4H2. Then they asked you for C5H12. Okay, so that would be 5 carbons and 6 hydrogens, and the value there is 178.4. And then finally C3H6, 3 carbons plus 3 hydrogens, and the value there was 20. Okay, so you've come up with all of your equations. That's the hardest part. So now you need to get what you want, basically. So this is what we want up here. So which equation is going to give us C12H26, the first one, but we need to reverse it. So I'm going to reverse that. Okay, so you get C2 and 13H2. But remember, when you reverse the equation, the value for the delta H has to, the sign changes. So from negative it becomes a positive. Okay, so that's that now. Now the next thing you want now is the C4H8. Which equation gives us C4H8? The second one, and it's on the right side, right number. So you just need to rewrite that. You have the C5H, so you have that now. C5H12 is the third equation. Okay, so you just write that out as it is as well, because everything's in the same, you have what you want and all of that. So 5 carbons, 6 H2s, and then finally C3H6. Again, you just rewrite the equation there, the fourth equation as H2, and that value was plus 20. Okay, now do you have everything that you want? Well, you have the C12H26, there it is, look. So I'll rewrite that now, C12H26. I have the C4H8 plus the C5H12 plus the C3H6. Does everything else cancel? Okay, so I'll use the grey to cancel. So 13 hydrogens. Now over here, look at all the hydrogens. You've got 4 and 6 is 10 and 3 13. So yeah, the hydrogen cancels. Now the carbons here, 12 carbons, and again here, look, you've got 4 and 5 is 9 and 3 is 12. So that's all fine. And then all you've left to do then is to add up the values, and when you do, you get 183.2 kilojoules per mole. Okay, so that's that question, right? Now, in the next question 2 there, then you were asked, they showed you there what term is used to describe compounds like A, B, and C below that have the same molecular formula but a different structural formula. Well, they're isomers. Okay, and then it says, why do A, B, and C separate in the same fraction? Well, if they have the same molecular formula, okay, then they have same molecular mass, and therefore they would have the same boiling point. So they would come out of the same fraction as a result in fractional distillation. 3 then says, explain which of A, B, or C is most likely to auto-ignite. Most likely, they asked you there, so be careful. So you would say A. Now remember the features of hydrocarbons that causes them to resist knocking, to stop them from auto-igniting. Short-chained, branched, cyclic. Okay, so your reason for saying A there is because it's the longest chain. Okay, no branching, something like that. Okay, then the next thing says, give the UPAC names for A, B, and C. Well, if you look at them there and draw them out yourself, right, you can see there's 5 carbons in A. So A would be pentane. B then is 2-methyl butane, and C is 2,2-dimethyl, because you have 2 methyls there, then propane. So they're the 3 isomers of pentane. Okay, now the next thing there, then it says in part B there, it says name the oil refining process where they're just using a general letter for W for the alkane, was converted into octane. Now octane is 8, okay, and when you like if you're unsure, draw out 8 and fill in the number of hydrogens, and 2 propenes, okay? Now, propene has the formula C3H8, but you had 2 of them. And again, if you're unsure about the molecular formulas, draw them out. But remember, for propene, you have to have a double bond, so to be something like that. And then how many hydrogens would you have room for? So you'd have room for 8 hydrogens, okay? That sort of thing, if you're unsure. Now, add up what you have there now. So you have, how many carbons do you have? So you have 8 and 6, that's 14 carbons. And how many hydrogens? 8 and 8 is 16. 16 and 18 adds up to 30. So that's what you had there. So it asked you to deduce the molecular formula of W. Oh, sorry, I'm after skipping part I of that. In part I of that, they asked you name the oil refining process. Now, lads, remember, I was trying to emphasize this in school as well. If you have more than one product, so here you have 3 products, so that has to be catalytic cracking. If you had W turning into an isomer, it would be just one product formed from W, and then that would be isomerization. So that example here is catalytic cracking, and we already deduced the formula for W will be C14H30, okay? Now, part C of that question then, they said to you, what's the advantage of adding tetraethyl lead? Well, they used to add it before to reduce knocking or to increase octane number, but we don't use it anymore because lead is toxic or poisonous, so we don't use it anymore in petrol. Now, then the last part of that was your thermochemistry calculation. So they asked you to calculate the heat of reaction for the combustion of 1 mole. So if I was you there, now you can always divide by 2 at the end, but I'd be inclined, I think, to divide by 2 at the beginning. So that'd be 13 oxygens, then you'd have 8 carbon dioxide, 10 waters, and 1 PBO. So that's what you want, because it's 1 mole. Now you can carry on and use the equation that they gave you there, but don't forget to divide your delta H value by 2 then at the end, okay? Now I just want to come up with show you how to come up here with the heats of formation. So the first one was heat of formation of tetraethyl lead. So tetraethyl lead, okay, looks like that, all right? So heat of formation of that. Now what elements are present? Carbon, hydrogen, and lead, okay? Now watch the ones there that are diatomic. Carbon's not diatomic, so 2C plus hydrogen is diatomic, so you have H2. How many hydrogens have you got though? Oh, sorry, I just noticed something there. We're about the 2 for a second. I'm actually just going to write the elements present and then we'll balance it. I think that might be a bit more straightforward. 52.7 is the value. So I have carbon, C, I have hydrogen, it's diatomic, don't forget, so it's H2, and I have lead. Now, balance that now. I have 4 times 2, that's 8 carbons. I have 4 times 5, that's 20 hydrogens. Okay, do you know when you balance it? Do you see what I'm doing? And then I have... when I do that, then I have, lead. I have 1 lead then there. So when you're balancing it, okay, so that's 1 lead then on each side then when you're doing that, okay? So 8C, I have 10 there. Did I take down that equation right? Sorry. So C2H5 4, that's a 4 PB, okay? 4 PB, all right? Okay, so then we'll carry on then, so, and we'll have, we were also told the heat of formation of carbon dioxide, so that's straightforward. Water is H2O, and PbO we need as well. That's minus 0.5, minus 285.8, and minus 219, okay? So when we do that now, so we have just carbon plus O2, hydrogen and a half O2, and then Pb plus, you have a half O2 there when you're doing that, okay? So C2, I'm just checking that formula again, H5 okay. So, I knew I had something done wrong. Do you know what I did there now when I was multiplying that? 20, but it's diatomic, so it's 10. I knew that wasn't working out for me. Sorry now. So 4 times 5 is 20 hydrogens, right? 20 hydrogens on the right hand side, but it's diatomic, so it's 10 H2, making 20 there. So the hardest part is definitely coming up with the equations. Now that you've come up with the equations, it should be a bit more straightforward. So the first thing you're looking for now, so what do you want again? So you want this here, so I have to reverse the first equation. So when you reverse the first equation, 4, that's a 4 PB, keep the arrows underneath each other, okay? HC, 10H2, PB, and don't forget you have to minus the value here because it was a plus, okay? So that's that, I have that. Now 13 oxygens. Remember what we said about oxygen? It's present in 1, 2, 3 of the equations, so I'm going to leave it, okay? I need 8 carbon dioxide, so I'll multiply this by 8. So 8 carbon, 8 O2, HCO2, and when I do that, then you have to multiply your value by 8 as well, remember, okay, times 8, and then I need 10 waters, so I multiply this by 10, so 10H2, 10 times a half, remember, is 5O2, and then that'll give me my 10 waters, and then again, don't remember, you must multiply that by 10, and finally the PB, you just need to write your, you just need to write the PB, so PB plus a half O2. Is that okay? Now, do I have what I want? Okay, so I have this, so that's fine, so that's that. Now, do I have the 13 and a half O2s? Well, I have 8 here and 5 and a half. So that's my 13 and a half O2s. I have my 8 carbon dioxides. I have my 10 waters, and I have my, oh Lord. And I have that, right. So does everything else cancel now? The 8C cancels with that 8C, the 10 hydrogens cancels with that, and the PB cancels with the PB there. And when you add up your values then, okay, you're going to get minus 6277.7 kilojoules